Good afternoon, Thibault in France, and good, I don't know, good grief for you guys in Australia, John and Behrooz. So thanks for hanging in there. We have speakers that are going above and beyond the call of duty. So I'm Nick Miller, longtime ESIG participant and troublemaker, I guess. So it's a pleasure to be here. And this session, I think you got to find really very exciting. It's appropriate that it's at the end of 2 days of discussion of what we know, what we don't know. And this sets the stage for today's talks on how do we learn the things that we've identified over the last 2 days about how we move forward. So we have 3 really good talks this morning on research roadmaps, and we have 3 of the premier organizations from 3 corners of the world, which is kind of cool, that are each going to talk about substantial and really important research consortia and plans to try to get all of these really complicated and consistently confusing arms and legs related to grid forming into some semblance of order so that the pieces can be explored and built and we can get the tools and understanding in the industry hands. I want you all to listen to these talks. You'll see simultaneously a substantial overlap, as you would expect. The physics doesn't change whether you're in the US, France, or Australia, but the philosophical approach and the details are different. And you'll see throughout these research roadmaps, both a tremendous commonality, but also different ways to have parse the problems and sectionalize them. There's lots of very cool graphics. That's obviously a critical part for all of these organizations to have the sexiest graphics. So we might even have a contest at the end of the morning to say who's got the coolest graphics. But I hope you'll enjoy it, and I won't talk much more. I'd like to introduce our first speaker, Dr. Ben Kroposki. He's the director of the Power Engineering Center here at NREL, so he's just up the road, and he is leader of this many things, but today's going to talk about the Unify Consortium. So Ben, take it away. You can use a lavalier or this guy.
Okay, thank you very much. And thanks everybody for joining us here, both in person and virtually. What we're going to talk about today is some of the activities that we have going on in the US, and specifically this thing called the Unify Consortium. So Unify stands for Universal Interoperability for Grid Forming Inverters, but you'll see that the Unify is the key aspect of what we're actually trying to accomplish too. So very important thought on this. So let's just talk at a high level what we're trying to do with this Unify Consortium. If you take a look at the graph over here, it's a graph that I use a lot that just kind of says, where are we now in the world with the amount of wind and solar, or you could translate that to inverter-based resource, do we actually have operating in the grid at any particular size? So system size from very small island power systems, let's just say 100 kilowatts, up to maybe 10 megawatts. That's about small island power size. Larger island grids, some of the Hawaiian islands range from 100 megawatts up to, say, Ireland, which is around 6 gigawatts. And then we have the big interconnects. I just listed the ones here in the US, ERCOT, and the Western Interconnect. One note here is you don't see things like California or Denmark on this graph because these are all actually independent operating systems, not interconnected to other parts. Western Interconnect and ERCOT are sort of, but we don't really depend on those interconnections. The other thing to point out here, the squares are instantaneous power, so at any point in time, and then the circles are annual energy levels, so how much over the year we get from wind and solar. And the key point here is at the smallest level, we know how to build systems that are 100% wind and solar, 100% inverter-based resources, and can operate through an entire year with just those. But as we get larger and larger, you see that kind of change a little bit. And so you start to see this decline in overall system amount of instantaneous inverter level, as well as the overarching annual energy. But what we've really focused on in this consortium is to figure out how do we actually make inverter-based resources and synchronous machines, which are the heart and soul of conventional power plants, how do they work together at any power level? So it doesn't really matter. From a power system perspective, we just put in inverters, they work properly. One of the things that we do point out here is that we have a big focus on grid forming inverters, which is not what the historic deployment of inverter-based resources in electric power grids looks like. We use a lot of grid forming on these small island power systems because you need something to form the AC waveform. But as we get larger and larger, we've developed and depended on grid following inverters. We really need to look at how if we want to basically raise that up so that we can allow 100% inverter-based resources at any scale, we need to understand how grid forming inverters fit into this picture. So this Unify Consortium really is focused on addressing these challenges with integrating grid forming technologies into power systems. And as I get into some of the details of what we're working on in this consortium, you'll see it kind of covers research and development, demonstrating these concepts at scale, developing best practices and standards, and developing educational material and training the next generation workforce. But in the near term, over the next 5 years, I propose that really this particular problem of getting us to close to 100% instantaneous levels with inverter-based resources is the critical problem to solve, because if we can solve that problem, then we can just start putting in wind and solar, and it should map into how these rules of the road allow us to operate grids. Now, one of the things that we were talking about here today is research roadmaps. There are a variety of people, and we'll hear some more people in this session talking about what's going on around the world in this space. But in general, when it comes to grid forming technologies, really there's kind of poor definitions of what specific capabilities are needed from these inverters to provide stable operating grids at any scale. So what we're really hoping to do is through this process, come up with some consensus around performance expectations and how we migrate those into actual product and then into deployments. One of the things I'll point out all the way over on the bottom left-hand side there, research roadmap for grid forming inverters, is a document that NREL, as well as Sandia, Lawrence Berkeley Lab, University of Washington, and University of Wisconsin put together now going on about 1.5 years. So at the end of 2020, we published that document. It was really a look at what are the needs inside grid forming inverter technologies. And that's actually where the Unify Consortium has spun out of. So that's a lot of the, if you want to know background material on where this all has come from in the US, a lot of it was collected from a series of workshops and then documented in that research roadmap. So that's available on the internet. You can go just search for research roadmap for grid forming inverters, probably the first thing that pops up. But as you can see, other places around the world, Australia, NSOE have started work in this space. Really what we're trying to do is how do we standardize some of these requirements in this process and educate the industry on how to make sure these types of technologies are deployed in a way that creates stable operating grids. Okay, so what is this Unify Consortium? The Unify Consortium is this consortium that we just started in January of 2022. So January 22, we just kicked this off. It started based on a DOE funding from the Office of the Solar Energy Technology Office, which is inside of EERE at the Department of Energy. as a 5-year project to get the ball rolling in this space. So we've basically laid out a 5-year plan that has a big component around the research and development necessary, how we demonstrate and commercialize the inputs that go into this space, and finally the outreach and training as an output to make sure that we can bring the industry together. And this term Unify, we called the Unify Consortium Unify because what we're really trying to do at the end of the day is unify the integration of inverter-based resources and synchronous generators together. If we can do that, then we create this pathway to get all these inverter-based resources and new technologies into the power system and operating properly. So let me walk through a little bit about what we're thinking here and how we plan to actually work in this space. If you take a look at this diagram, the first area over here where it says balancing area, imagine that this is the power grid with a variety of different resources on it. So you may have individual inverter-based resources. You may have plants where we aggregate things together, or you may have aggregations of inverter-based resources at a variety of scales. And one of the things that we are focused on is how do we develop the actual input and output signals that may be coming from the system operator, but as well as pairing those with a set of controls that are built into the inverters themselves. So inverters are going to have these autonomous level of controls. The challenge with inverters is that you can pretty much program them to do whatever you want them to do. So how do we marry that controllability with the rest of the power grid? And that's our biggest challenge. Then how do we exchange these signals with a system operator of the power grid? And then how do we allow for things to happen like distributed optimization and control of all these devices that get distributed in a power grid? At the end of the day, we're going to need advances both at the individual inverter level and at the system level. But what we're trying to do is tie those together. And so that's something that we're calling Unify Specifications, for lack of a better word. It's these specifications that are going to standardize the performance of how inverter-based resources connect into the electric power grid, and specifically provide all of the services you would normally get from synchronous generator devices. So you're going to need a set of system level guidelines that are telling you how to maintain normal system operations across grids. You're going to need a set of inverter level functional requirements that the inverters need to meet. And we're starting this process of building out these specifications. So right now we have sort of a draft one that we're working internal to the consortium right now. But over the next several months, we plan on making that available as a set of specifications to start enabling this. This will also drive a lot of the work that we're doing on testing, evaluation, and demonstration in this area. So how are we currently set up? This is how we are currently set up. So NREL, the University of Washington, and EPRI co-lead this consortium, but we also have an internal leadership team made up of specific advisors across all of the areas that I list down here below. And then we have an external scientific advisory board, a DOE review board, since this is a DOE project. But the key thing down here is you can see those three areas. We have inside each of those, we have working groups working on developing sort of that particular space. So I'll talk about some of these, but you can kind of get an idea of where we're heading in this area. So again, we have working groups that we formed inside the consortium where we're defining specifications, we're looking at models, controls, hardware, integration validation. I'll go through some of this in a little bit more detail here. And you can see our current set of project members. So NREL and EPRI, along with 3 other national labs in the United States. We have 12 universities that are plugged into this. And then on the industry side, we have a variety of vendors, both for inverter technology, hardware in the loop evaluation technology, and then a set of system operators and utilities that are involved. In addition to that piece that I just showed you, which is the formalized DOE project team, we actually are trying to work outside that and bring in other expertise. For example, say the software vendor community that provides software solutions to most of the power system applications around the world. We're making sure that our modeling and simulation work has a pathway to get out to those industry provided projects. And then we also are working closely with a number of additional inverter vendors, because at the end of the day, they're all going to have to be on board with sort of these rules of the road that get developed. And finally, there's a variety of consortia, including ESIG, G-PST, PCIRC, Freedom Center, some other places around the world that are heavily doing research in these type of applications. So making sure that we're sharing information around the world in this area. So as we look, I'll go through this. How much time do I have left?
About 10 minutes.
10 minutes, okay. So as we go through here, I'll go through a little bit more detail. So one level detail on each of these areas, just to give you an idea of where we're heading in this. Remember, we just kicked this off in January. So I would say everything is a work in progress, but what you'll see is kind of a pathway of where we're going in this area. So in the R&D area, modeling and simulation controls, hardware integration and validation. Inside the modeling and simulation area, so we realized that validated models for inverters is a tricky subject right now, mostly because of the fact that it's difficult for vendors to just open up all their control algorithms. At the same time, we need to understand how inverter-based resources react to a variety of grid conditions. And so we're working right now on developing models, as well as a model library that people can use all the way from EMT, electromagnetic transient modeling, out to steady state modeling. And then we're partnering with the various vendors of this to come up with pathways to pass these models and simulation programs that we develop inside this consortium out into industry. In the controls area, you know, when we talk about grid forming technologies, there's right now there's a lot of pathways for developing grid forming controls inside inverters. There's probably 4 or 5 different known ways of doing this. And so what we're trying to do is come up with basically generic primary controls that would be embedded inside your inverters that people can use as a platform. We also are looking at secondary layer controls, so something similar to automatic generator control or AGC that would get passed down from utilities. What kind of information needs to pass? What type of control algorithms are best used for doing this? So we have a lot of work in this particular space. In the integration and validation area, the project team has a pretty extensive set of testing and characterization facilities across the institutes. But one of the things that we're really looking at is developing use cases that span all the way from microgrids to bulk power transmission system level of how to integrate grid forming technologies. And then looking at how you would validate some of the performance of these different types of systems. So we're spending a lot of time right now developing use cases that would map to some of the testing and evaluation capabilities we have across the US in this area. One highlight that I'll just mention that in year 3 of this particular project is we're planning on doing a large-scale experiment at the Energy Systems Integration Facility. This is located here in Golden, Colorado, but we have the ability to bring in lots of vendors. So the idea here is multi-vendor experimentation. Right now, today, if I was a single vendor on a single power system, I can build a grid forming inverter system that will work. But one of the things that we really need to validate is, can we just have any vendor follow a set of rules and then all the inverters all work together, share power, and do that properly? That's what we're going to be setting up in this facility, is this kind of test bed where we'll be bringing in multiple vendors that are all sort of following the rules, but we don't know the actual innards of all their control algorithms, and making sure that they can provide stable grid operation at a variety of different contributions from inverter-based resources. So in addition to that, we're looking at how to push this into industry. So I'll talk a little bit about some of these areas here, specifically the 20 megawatt demo, but we also are looking at what IP is needed around grid forming technologies and what can be specified in this space, and then how to push this into products and standards. So first off, on the 20 megawatt demo, this is a requirement by the end of our project that we will demonstrate these grid forming technologies at a demonstration site at least 20 megawatts. Now, we are in negotiations with a bunch of the utilities that are partners on our project to look at things that range from large scale merchant plants that could range from 20 to 200 megawatts. Right now, we're putting large scale wind and solar plants in the US at hundreds of megawatts. And what we would like to be able to do is influence grid forming technology into those deployments, but also like high penetrations of distributed resources. And so we're looking at opportunities in that space where we can have smaller inverters and different varieties of technologies. Those kind of sites, what we're, our wish list, I'll throw it up here as if you are a system operator or a system integrator and interested in being part of our demo project, please let me know. But this is what we're looking for, is we're looking for sites that include a laundry list of interesting things, multiple single and three-phase resources, mixes of grid following and grid forming inverters, wide range of power conditions, wide range of source side energy sources. And what we would like to validate through, especially during commissioning and other testing processes, is this scalable controls, voltage and frequency controls, power sharing, black start capability, how these devices handle transients and the like. So a lot of interesting things here. Again, I'll just throw it out there. If you are aware of any kind of sites like this or interested in talking with us, please get in touch with me. I'll just mention quickly that we've done lots of work along these lines, mostly on grid following inverters providing reliability services. So as an example here is a large 300 megawatt plant in California providing AGC type regulation services. But what we're looking for next is the grid forming capability piece. On the IP management side, one of the things we're looking at, I'll just mention quickly, is that we're trying to identify all the IP in the grid forming space in such a way that people would know if they need to access any of that IP, whether it's available or not. And on the standards front, one of the things that we're most recently doing is working with the standards development organizations to see how grid forming fits into the existing standard fleet, if you will. So things like IEEE 1547, which is interconnection rules at the distribution level, and the newly published IEEE 2800, which is inverter-based resources at the transmission level. Neither of those really completely adequately cover grid forming inverters today. But what we would like to do is take our lessons learned and plug those into the standards as they get revised. 1547 just already started their revision for the next round. So we have a way of mapping into the existing standards. Hopefully we can take advantage of that instead of writing a whole new standard on grid forming technologies. Education and outreach. Obviously, I'll hype that we're also hosting the IEEE PES meeting. We're also having a Unify meeting in association with that. And there's a variety of education and outreach stuff that we're planning on in this space that we're going to be doing over the next several years. One thing that I will highlight is every spring and fall, we host a Unify seminar series. We're on summer hiatus right now, but we'll start back up in the fall, where every single week for 15 weeks, we have a talk on grid forming technologies. We've had roughly 30 talks over the last year in this space, and we have about over 1,000 people registered for this seminar series. We get about 250 people every week attending, so definitely a hot topic in this area. Okay. So how do you get involved with Unify? We actually have a paid membership structure that allow people that weren't part of the original project to join in. There's a variety of benefits. Probably the biggest one is really this being at the front end of the development of the specifications work, and then tying into the validation, experimentation, and deployment work that goes along with this, as well as the training and educational materials. We are on LinkedIn. If you look up Unify Consortium, if you want to get on our little internal mailing list right now. Okay, with that, I'll say thank you and take any questions.
Thanks, Ben. I'm going to hold most of the questions to the end, but if you got any quick clarification type questions for Ben, we can entertain those now. Pretty exciting stuff.
Yep.
All right, I can let everybody process.
Yep,
So,
processed and happy to
all right.
answer questions moving forward.
So our next speaker is Thibault Prevost from RTE, the ISO, or at least the grid operator in France. And Thibault's been working in this space, very well-known stability expert. And he is going to take us through the RTE roadmap, and you'll see that, as I said, quite a bit of overlap, but also they sliced and diced things a little differently. So with that, Thibault, we got you.
Hello, everybody. Yeah, can you hear me correctly?
Yes, you sound good, Thibault.
Great.
Go to it. You got about 20 minutes. I'll
Okay.
nag you when you get to the end. All right.
Yes, thank you. So thank you, Nick, for the introduction. So as Nick said, I'm going to give you an insight about R&D, about grid forming. Maybe I will start with some context on the French situation, because you might wonder why we are looking at grid forming, why today we have a lot of nuclear. So presently we have 60 gigawatt of nuclear and just less than 30 gigawatt of power electronic connected. On the grid, energy-wise, it's even worse, because as nuclear is base load, it's representing almost everything. But quite recently, there was a study about energy forecast for 2050 with different scenarios. And if we quickly go through them, for example, the first one is with, so they all meet the 2050 net zero carbon goal of the European Union. This one is with distributed energy. So we see that as most of the household want to produce their own energy, it's mainly photovoltaics. We are here in a situation where in 2050, we have more than 200 gigawatt of photovoltaics for only 15 gigawatt of nuclear left. And we have 100 gigawatt of cumulative wind. Other scenario where we also have no new nuclear and a lot of renewable, but it's more wind, a bit less of photovoltaics. We have 100 gigawatt of photovoltaics and 150 of cumulative wind. And then we have other scenario where we will build new nuclear, but even in this case, here, for example, is the case where we just built 13 gigawatt of new nuclear. We still have more than 200 gigawatt of power electronic connected generation. And even in the scenario with the highest share of nuclear, here we have in 2050 still 50 gigawatt of nuclear. We have more than 150 gigawatt of power electronic connected on the grid. So in the end, for any of the scenario, we will reach at some time very high penetration of power electronic devices. And will we be saved by our neighbors? Not so sure. So this is a situation for Europe, and we see that for any of the scenarios that have been studied in 2050, we have almost nothing left as rotating machine, just the hydro, I would say. So there will be hours a day with very few synchronous plants, I would say even zero synchronous plants. So we need to study grid forming. So about the recent research, I will first mention the Osmosi Project. You might have heard of that because my colleague Carmen presented it yesterday. So we had 2 demonstrations in one of the work package. One demonstration was in a collaboration between INGE team, inverter manufacturers, and RTE. And the aim was to take off-the-shelf hardware and to see what can be done by just changing the controls. So it's a hybrid storage where we have both battery and ultra caps. The aim was also to check that even with the batteries that have a low transient capability, we can still manage grid forming and see what can be done with that. And we had another demonstration at EPFL. EPFL, it was an existing battery that was there for several years. It was not supposed to be operated in grid forming, but they add what was called this VF mode, and they had to build some outer loop on top of that to quickly update voltage and frequency reference to make it behave grid forming. So the idea was really to understand what can be done with existing hardware, even already installed hardware. So we had many technical results. So probably have been presented, like how does our installation behave in case of phase shift if we have both battery and supercaps, only supercaps, only the battery. How does it behave where we emulate different inertia level, if we emulate different transient grid forming level, how does it behave for different unbalanced condition. So this is very interesting technical result, and if you are interested in them, they are all public and you can download them. But I would say that even the most interesting work is also the work that has been done on the specification of the different, in fact, services that can be proposed by grid forming. So in fact, we try to divide it in 4 types that build upon each other. So the first type is a standalone capability plus system strength, which means that if you have a voltage amplitude change, you will provide very fast current for a very short amount of time. And you can operate in a wide range of short circuit ratio. It's very interesting because basically it has no cost. It's only software update. And it's critical where you have low system strength locally. Then type 2 is type 1 plus what we call synchronizing power profile, which means when you have an angle shift, you need to provide a peak of power for a very short amount of time. It's necessary when you have inertia that decrease locally. For example, if we keep rotating machine in Central Europe, but for example, in Spain, you just have photovoltaics and wind, you don't have inertia issue at European level, but you would still have issue in Spain if you don't have this kind of grid forming. It has very limited cost because it's a very small amount of energy needed. Then you have type 3, where you provide on top of type 2 inertia response. Therefore, you need a bigger amount of storage, few seconds, maybe a few tenths of seconds. And then you have type 4, when you do type 3, plus very high fault current, more than 2 times nominal currents. Why do we believe it's necessary to have that? Is because we need to make best use in the future of the existing capability. So there is still work to be done on harmonizing the requirements, definition, but we know now that in fact grid forming is a set of different capabilities that can be provided. If we have separate definition for each of them, it will allow to make best use of existing capability. Let's take the example of a battery, HVDC, STATCOM, photovoltaics, and wind. They all have inverter. They can all be, in fact, kind of grid forming, but they do have very different characteristics. Photovoltaics and STATCOM probably have a very small amount of storage embedded. Wind, they do have maybe some inertia from the rotating blade. Batteries, they probably have a huge amount of storage. HVDC, it would depend if it's connected to another synchronous area or if it's connected to the same synchronous area. So the idea of having this different type of grid forming and this cumulative one is you can require what's doable at no overcost. And I would say that in the next version of the European RFG, which is the requirement for generator, the door for the installation of grid forming unit will be open. So which means it's not finally voted, but it won't be mandatory, but it will be possible to have it. Other work that has been done within RTE, it's the Ringo project. So Ringo, in fact, usually should be a grid following type of battery. So we have 3 batteries used as virtual line, but as we add this battery and inverter on the grid, we run a grid forming experiment where we black started, in fact, a part of the grid with transformer and successor cable and 20 kV cables. We started a wind farm. We operated it in island for a few hours, and then we seamlessly connected back to the main grid. And and switch back in grid following mode. So this is kind of dirty image, but I didn't find any better quality of the two frequency and the reconnection here. It was eventually no impact when reconnected, very smooth transition. So this was the research achieved for now. Now, what is the ongoing research and research needed? So for example, we do have HVDC. In fact, France-Spain interconnection can provide grid forming capability for black start. It can even be used in grid connecting mode, which means not in black start. Even in the transition period from when you restart a small area, you can operate in grid forming, even if you are connected at both sides on the same synchronous area. For now, it's just made for transient operation, but it's doable. And we do have research project now to get the most out of HVDC, because in fact, HVDC are usually TSO owned. And so it means that we can in an easier way specify grid forming on that. And I would recommend you to go on the HVDC Pro project. So it was a project where RTE was involved. It was held by Syntef. And we have a lot of study about what can HVDC provide as a different grid forming services. And we also have a PhD with KU Leuven working on the implementation on grid forming, but on bipolar HVDC to see what are the different configuration possible. For example, if you have bipolar, we can have one pole operating with one end in grid forming that would be on the east side, and on the other pole, the grid forming on the east side, which would mean having a grid forming HVDC on both sides. Grid forming and unbalance, for us, it's a very important topic. Up to now, most of the study have been investigating grid forming in balance situation. For osmosis demonstration, we had to take into account that the voltage on the system is not balanced. So we studied a bit the unbalanced situation, both in normal operation and during fault. And in fact, we ended up with the fact that specification is a key. It's very tricky to know what is needed. And I mean, do we want balanced voltage? Do we want balanced current? Do we want mixed solution? Do we want the same for any time of the day? Does it changing depending on what your neighbors can be doing? If you have a synchronous machine close to you or not, if you're in a remote area or not, it's tricky to specify and then to apply. On this subject, there is also, but you probably be aware of it, a PCR project where we are participating about the operation of inverter in grid forming in unbalanced condition and its impact on the protection. There is also the question of where and also when they are needed. So presently, if you want to assess and demonstrate the need for grid forming, it requires detailed studies. We can't do this detailed study for any of the situation because in the future we now do probabilistic situation. So we need to have indicators to screen where we will need this grid forming. So presently there are existing indicators like SCR, weighted SCR, SNSP available for current, but they don't really accommodate for the presence of grid forming inverters. So when you start installing grid forming inverter, you don't see the impact of them of the different indicator, or you don't know if it's really, this indicator are really suited to take into account the impact of this grid forming. So there is already a PhD that is just starting working on that with L2EP, a lab in north of France for optimal placement of grid forming and grid following, and also to develop these indicators. Ben also mentioned work at NSOE levels. So we published a paper on high penetration of power electronics in the system, but within the next year, there will be also a roadmap for the research and the stability management of European system in a power electronic dominated mix. So I can't tell you exactly when it will be published, but we are presently working on that. As an interesting also, I think, future research is, should grid forming be exclusively for generation? Because in fact, there is a priori no barrier to have grid forming inverter connecting DC loads. And if we have grid forming capability on big P-connected load, it would widen the pool of potential grid forming inverters on the grid, would make it stronger and would make it even more resilient. Sorry. Eventually, also there is a big debate on capability versus use. So having enough grid forming capability on the system is of paramount importance, because if we don't have enough grid forming on the grid, I mean, grid forming includes synchronous machines that provide the same services as grid forming. You don't have a grid because it would just be unstable. So we need to ensure that we can have it at any time. So in fact, the capability of being grid forming should be required from any unit up to its nominal capacity, so to prevent overcost, even if the use might not be always necessary. I mean, we need to have any unit being capable of doing so, even if we don't ask the unit to actually be grid forming within the next 5 years, and even if after that we don't require them to be grid forming 24 hours a day. There is also the question of should we have a market for grid forming, or should it be a requirement? And I think it will also, this question is quite tricky. It will also depend of what do we call grid forming, because for example, we mentioned that type 1, 2, 3, 4 grid forming, type of grid forming. For me, for sure, the lowest type is basically something very similar to FRT. We don't create a market for fault right through. Any unit that needs to connect on the grid needs to be able to withstand the fault. So the market question might be open in the future, but in fact, we can't have a market for the capacity. We can have a market for the use of it, but not for the capacity. And maybe it should also be interesting to question the fact that if we need to pay for the one that produces its kind of short circuit power, maybe the one that consumes it could also pay for it. So peer-to-peer market of short circuit power. And with this grid forming, we also need to explore new operation of the system. Basically, I'm especially thinking of distributed system operation, because for now, distributed operator, they just want distributing unit to trip when there is an issue on the system. Now with a grid forming unit on it, they can in fact be operated in island. They can allow subsystem to be operated during partial blackout, while presently they would probably be blacked out too. We can also think about restarting the system bottom up. We also have on that a PhD working in collaboration with the lab and with the main distribution system operator to see if we can have grid forming on distribution side to ensure that in case of major event, we can have some pocket of the distribution system that would stay alive and would restart the transmission system out of it. We can also try to develop new defense plan. For example, in France, we have specific defense plan where in case of a loss of synchronism or very stressed situation, we can split the system in subsystem to avoid the spread of the issue. With grid forming, we can again rethink this defense plan. And as I mentioned, we definitely need to think a new operation of the distribution system.
Well,
that's it from my side. Thank you very much.
Beautiful. I was just going to nudge it to wrap up. That was perfect. Thanks, Thibault. We can entertain. Yeah. So be careful about that. If you have any quick clarification questions, otherwise we'll save things to the wrap up. Okay, our final speakers, which maybe we should have made you first. I suspect now it's really late in Australia. So we have two speakers that are going to talk about the CISIRO research roadmap from Australia. So AEMO has, as you've heard continuously for the last 2 days, is in the eye of the storm. And there's a lot of great work taking place in Australia, and they're trying to stay connected with the activities of the rest of the world. So we have two speakers, Professor Dr. Behrooz Bahrani, who is originally from the École Polytechnique Lausanne, and now he's director at Monash University, leading work in this area. And then our second speaker, Professor John Fletcher, who's now at University of New South Wales, having come from Strathclyde, and he's director of a number of different pieces of relevant work that's going on at New South Wales. These two distinguished gents are very well connected with the grid operator and all the drama that's taking place in Australia. It's the middle of the night for them, so extra thanks for the heavy lifting of accommodating our schedule. So I think, do we start with Behrooz? I'm not sure.
I guess John was supposed to start first. John, would you?
Okay, John.
Would you please start?
I hope.
Sure, absolutely.
All right. Did you finish off the glass of whiskey? Or maybe you
I
said
did, yes. I'm ready for another one, that's for sure.
Yeah, right. You will have earned it. Thank you. Okay,
Thank
onward.
you. Thank you for the introduction. So I'm Professor John Fletcher at the University of New South Wales. I look after a lot of things at the moment. Along with that, I'm supporting the CSIRO and AEMO road mapping activity and the development of a range of topics which are shown on this slide. The one that I'm particularly involved with is topic 9, which is one of the topics that are really specifically focused in terms of the G-PST roadmap, specifically focused on, if you like, the Australian angle of things. In Australia, we've had a real boom in distributed PV. We're now sitting at a system that has about 10 gigawatts of distributed PV, so rooftop systems installed in a system that has a peak demand of about 35 gigawatts. And there are states in Australia, particularly South Australia, that at times are running for numbers of market timings on purely IBR, which is really quite astounding. And there are some very interesting things going on in the Australian network that you've probably heard through the conversations you've had. Now, the distributed PV is not grid forming, it's all grid following. But it's important to recognize, particularly in Australia, that we have a system where the demand centers are few and far between, but they're large, and installed in those large areas of demand are quite large numbers of distributed PV systems. And of course, that inverter-based resource narrative is just going to increase over the years as we embed more and more inverter-based resources, including batteries, EVs, hybrid systems, and of course, potentially converter-connected loads. And pretty much anything that's connected to the grid has to have some form of oscillator, and that oscillator is always going to be vulnerable to particular types of events. So we probably all know by now that rooftop inverters misbehave. Here's an example of a 5 kVA inverter tripping off in 1.5 cycles with a relatively benign phase angle jump of 30 degrees. This was work that we did at UNSW as part of a bigger project with AEMO, where we set out primarily to develop a model that the transmission network operators could use that modeled to some extent the distributed PV that they would be transmitting their bulk energy towards. And up until the time we started this work, there was no real understanding of how distributed PV could impact the wider network. And the narrative really here is that this really scared AEMO. We calculated that about 30% of the inverters that were connected to the grid, connecting rooftop PV systems to the grid, were vulnerable to relatively benign grid disturbances. And that kind of represented a 3 gigawatt contingency for AEMO, which is something they just hadn't been considering before. So it just goes to show how you can really get yourself in a sticky situation very quickly with the great advances of distributed resources. And that was a project that we ran at UNSW. It had a load of really interesting impacts. Obviously, we discovered some of the vulnerabilities of PLL, so we went about devising a system that is better than a PLL. In fact, a system that allows inverters to resynchronize in one cycle. The work that we did led to a change in the standard in Australia. That's AS4777, and that new revised standard is the 2020 standard. And of course, it's 2022 now, and we're already seeing some of the frailties of that standard and the changes that we have to make. So that's kind of not grid forming, but it tends to show how much scrutiny we really need to put into our understanding of how the practical hardware actually functions when it's connected to a grid. And that leads on to this quick example of some of the work we've been doing at UNSW on grid forming, and specifically the use of real-time systems with control hardware in the loop to de-risk some fairly large investments in equipment. This particular example is looking at a grid forming battery energy storage system connected into a weak area of the grid. Weak in Australia is pretty much very weak by anyone else's standard. This particular system is a few hundred kilometers down a transmission line from pretty much nowhere to nowhere. But at the end of this line, you can see that there are a number of installations. There's a couple of solar farms, there's a wind farm, and all of this is out there to supply mining loads as an example. And this particular part of the grid suffers from an oscillation in the voltage, which can be up to 5% with a frequency that varies somewhere between 7 and 19 hertz. So it's a real problem for that part of the network. And we looked and helped an organization who owns some of the assets out in this area of Australia. And we looked at using a battery energy storage system with a grid forming control capability on the inverter. And what we did was basically we took the control hardware and put it in a hardware in the loop system. So fairly standard approach. We did couple up 3 different types of hardware in the loop systems in order to do this: an RTDS system, an Opal RT system, and a Typhoon HIL, all operating at slightly different sample rates. The power system runs at 50 microseconds. The inverter is represented by a system that operates at about 2 microseconds, and then the inverter controller at a microsecond, which is about as good as you can do with the current technology. So that multi-vendor approach was implemented. We put it all together, and we could demonstrate to the government organization who's going to fund this work that it was worth putting the money in, because our simulations could demonstrate that this oscillation out on the system could be remediated by using a form of grid supporting functionality. And these slides really show that process that we demonstrated using the real-time digital system and the simulation and the modeling capability that gives you. And we could then show how different levels of inertia and damping could operate this system stably, and primarily show that without installing the battery energy storage system with the grid forming capability, without that, then you'd still be having these oscillations. So there's a summary of the outcomes, and part of the work that we're doing out here in Australia is centered around that distributed PV. And I think one of the key issues that we're probably all going to face, and this is really the main point of this particular slide, is the development of workforce and the requirements that we're all going to need in terms of workforce and the capability of assessing what are really very complex issues on grids, particularly in places like Australia that don't necessarily benefit from having a large mesh network, where some of the aggregate techniques that other nations can focus on don't really hold much water for us here in Australia. So that's an important aspect that here we are thinking about, and looking at other nations with similar networks to Australia, and making sure that through something like the G-PST we can spread the knowledge, and that knowledge sharing activity is a really important part of what we do. And with that, I'll pass over to my colleague Behrooz, who will tell you a little bit more about some of the other work that's going on in the G-PST consortium out here in Australia. And thank you.
Thank you so much, John. Let me share my screen. Okay, I believe you're seeing my screen properly now. So I'm Dr. Behrooz Bahrani. I'm the director of the Grid Innovation Hub at Monash University. And I would like to present what the work that we've done over the last year. Thank you so much. So I would like to talk a little bit about the research roadmap, research plan that we were part of that last year in Australia. Was supported by G-PST-CSIRO and AEMO to develop this research plan. I guess John explained a little bit different topics that were involved. And UNSW and Professor Fletcher were involved in DER and stability, and we were mainly responsible for task 1, which is on inverter design. And I would like to walk you through that, a little bit of the work that we've done, and the research questions and problems that we have identified. And towards the end of the presentation, I'll be talking about one of the example research projects that we're currently doing as part of this research plan, very recently funded by CSIRO. Well, inverter design, I believe, as the name suggests, is the aim of the task is around various areas around inverters, control design for inverters. Well, obviously, there is no secret that they are increasingly being dominant in integration of solar and wind energy into the grid, and the rate of new connections, particularly in a country like Australia, is outrageous, and it is actually putting the operation of the grid at risk. A lot of security issues, and still there are so many unanswered questions around IBRs. Again, particularly in a grid like Australia, which is a very skinny, weak grid, very different from the rest of the world. Quite a lot of these problems are unique and still unanswered. And the aim of this task, task number 1, inverter design, is to contribute to the secure operation of the future IBR dominant grids by solving these unknowns around IBRs. Well, significance and contributions to the Australian context obviously are around alleviating the risks around these connections and hopefully secure operation for the future of Australian electricity grid, particularly improving investors and developers' confidence around connecting new IBRs to the grid. As we speak, there are quite a lot of projects going on in Australia which are facing different challenges when connecting to the grid. Obviously, we have a lot of different tests before connecting IBRs to the grid, but still that's sometimes not enough because of the very strange challenges that we've got in our grid. And we're hoping by answering these questions, we can assist future developments in Australia. And obviously, by retiring the older synchronous generators, which is already happening in Australia, these problems will be pronounced further and further. So what we did last year to actually develop this research plan, we interviewed quite a lot of different stakeholders from different parts of the industry, from system operators, network service providers, manufacturers, AEMO itself, through a very, very systematic, structured interviews. And based on our own expertise and research projects that we put together a long list of questions, categorized them into themes, 40+ questions, and then based on these questions, we identified 5 major tasks to be included into the research roadmap, 14 subtasks, and we also identified, obviously, the shared tasks with other G-PST topics that John showed earlier. This is a long list of the stakeholders that we actually engaged with last year, representing, like I said, the grid operator, manufacturers, consultants, TNSPs, and this here is a word cloud that shows which topics and issues appeared the most in our interviews and in the questions that we developed. Out of the interviews and questions, we, like I said, identified 5 major tasks: frequency stability, voltage stability, interaction mitigation and oscillation damping, protection, reliability, and emerging trends and topics. And there are certain, obviously, links between the tasks that we were looking at and other tasks that our colleagues were looking at. And mostly relevant to grid forming, I believe, was this emerging trends and topics that we categorized grid forming technology into this task. Here is a longer list of the tasks that we have identified for frequency stability. Essentially was around defining advanced IBR and storage system frequency response requirements and capabilities for future grids. Voltage stability, investigate the reactive capability and voltage control requirements. Interactions, particularly very important for us, identify and resolve the source of adverse interactions. And again, here grid forming come to actually the picture a little bit, because interactions often are more pronounced in weaker parts of the network, and grid forming inverters can obviously help and assist in mitigating these interactions. Obviously, a lot of these interactions go back to the controllers of your grid following inverters at the same time, but obviously having grid forming can assist. Protection, reliability, determine and propose mitigation methods for the adverse impact of IBRs on protection of power system. And like I said, trending topics, grid forming was appearing quite a lot in that trending topic task that we put together and we identified. Now, after identifying and developing this research roadmap, this year we are again working with CSIRO and obviously other research organizations, international and also national in Australia. We're trying to execute some of these research problems and research projects that we have identified. We will be again involved in inverter design topic along with a few more topics, but I will be focusing on inverter design. This is one of the, what I would like to talk about now is one of the example research projects that we will be executing over the next year. And that's around IBR's transient stability. Well, obviously, as you know, during and after fault, large transient occurs, and And typically transient stability methods are employed to look into this transient stability. And often people look into these from a SMIP point of view, single machine infinite bus. You can use EAC equal area criterion method or phase portrait method, Lyapunov's method to look into the transient stability. But what is actually more challenging and more interesting to look is that if you've got a more complex system in which you've got a number of IBRs, the IBR response is not only governed by their controller, but also by the interaction with other assets that you've got in the network. So if you've got a larger system, then the oversimplified SMIP model that you might have is no longer accurate enough to look into that. And the project that we will be working on over the next year will be actually developing transient stability analysis methods and also obviously enhancement methods based on the analysis that we do applicable to multi-IBR systems, and particularly in the presence of grid forming inverters. So what we are looking at here is a parallel grid following and grid forming inverter. And we first will start obviously with a simple system in which we have one inverter, one IBR equipped with grid following and one with grid forming control, and we will study its, the transient stability of this parallel system. And then the plan is to move into a multi-clustered wind farm equipped with distributed grid-forming battery energy storage systems. So assuming that you've got a large wind farm and you've got clusters, and we would be putting different, smaller grid-forming batteries in the wind farm. And we'll study the transient stability using the method that we would be developing. Well, to be honest, we have actually developed the first one already, and we will be applying that first one into the multi-inverter one. And we are hoping then to take it out of a wind farm and look into a region. We are expecting that the scenario of a multi-clustered wind farm would be very similar to a region. The difference obviously would be that in a region, you don't have only wind farm and you don't have only wind turbines, you also have solar, and we'll be adding those to the mix. This is a simplistic view of the larger system that we will be looking at. So the idea is to have different clusters. In every cluster, we will be having a grid following inverter, and then a virtual synchronous generator or grid forming inverter, and maybe other grid followings. And then these clusters will be connected to a common bus and then integrated to the grid. In addition to this, we have another project which is ongoing at the moment at Monash. It's a project funded by Australian Renewable Energy Agency. We're working with AEMO and one of the TNSPs in Australia, AusNet Services, and Hitachi Energy as the industry collaborators, and we're looking into the integration of renewables into weak grids. A big part of that project is also grid forming capabilities, and we have been working on developing different types of control for grid forming inverters. And obviously, yes, we've been working on grid following control as well, and proposing enhancements to existing grid following inverters. And at the moment, we are towards the end of that project, and now we're looking into the application of the methods that we have developed for the grid forming and grid following inverters to a particular part of the Australian network, which is a very problematic and weak part of the network. We're hoping to actually shed some light into the problematic areas in that part of the network, and we're hoping by replacing some of the existing inverters and IBRs in that part of the network with the solutions that we have developed, we are hoping that we can solve some of the problems. And well, an example of the problems happening in that part of the network, for example, is certain oscillations at certain frequencies, sometimes around 8 Hertz, sometimes around 19 Hertz, occur in that part of the network. And we're hoping by our solutions, we can eliminate this. For more information, if you're interested in this project, I've put a link here. It's actually linked to the project, and this is where we share the publications of the project. I guess that concludes my presentation. Back to you.
All right, thank you,
Yep.
Professor Bahrani.